And they do it at science centers, at institutes that are related to Rosetta. And there are events organized in Switzerland, in Austria, in Italy, in France, in Germany, and in Spain. So welcome to all of you who are watching us now. The program itself has two main target groups, the media, but also the general public. And we have a lot of leading experts today here on stage that are covering the science aspects, the operational challenges, and also the programmatic topics. And even more important, there are always breaks in between, and you will have ample time to do a lot of interviews. So an ideal stage for you to engage with the experts we have today here. We would have liked to invite the public here to come to ESOC, but of course that's not possible because the center is an operational center and we don't have enough space. But we have been inviting the public to join us, and as you know, we have a competition, a video competition, social media video competition running. It's still running, so please have a look at facebook.com Rosetta Mission, and you can still upload some of these videos. And a lot of people did already, and I have to say the videos they're just beautiful. They are really, really creative, and they are really, really heartwarming, and they're very encouraging for all those people who have been working for decades on Rosetta. So thank you very much for those videos. They are just great. Keep on loading those videos up to our platform. Now our program will start in 1 minute, and we will start with two presentations. The first one is by Thomas Reiter. He is the director of Human Spaceflight and Operations at ESA, followed by Alvaro Gimenez. He is the director of Science and Robotic Exploration at ESA. And then we are going to switch location, and we go straight into the master control room where my co-moderator, Monica Jones, will lead you and guide you through a program with reports and interviews. The interviews are given by our Director General, Jean-Jacques Dordain, and then by Paolo Ferri. He's the head of operations at ESA, and Paolo Accomazzo, who is the spacecraft operations manager. And then we have also the lead scientist of ESA, Matt Taylor, and Mark McCaughrean, who is the senior scientific advisor in the Directorate of Science and Robotic Exploration. That program will be also visible here on the screens. It's also live on ESA TV, so you don't have to change location. We will go straight in to the master control room with ESA TV. And then we do basically a question-answer session, but when we go back from the master control room, it will be the chair of the German Aerospace Center and the chair of the ESA Council, Johann-Dietrich Wörner, who will address you. And after that, we do a question-and-answer session, so with all those that you have been seeing so far in the program. And then, of course, there is a lunch break. And afterwards, at 2, we do scientific presentations back here on stage with the lead scientists of Rosetta. There's Joel Parker, Jean-Pierre Bibring, and Wlodek Kaufmann. And the information will be completed by information about the spacecraft. And we also want to tell you a little bit what's the difference between comets and asteroids. And there we have Stefan Ulamek, we have Norbert Peiler, we have Gerhard Trollshagen and Gerhard Schwem for covering that topic. And in between, we will also keep you updated on the operational progress. And Andrea Accomazzo and Paolo Ferri will do this. And well, of course, we hope that the signal will come between 18:30 and 19:30. That program, again, will be live on ESA TV. And I am really, really happy that you've been joining us today. So thank you for that. And I wish all of us good luck with the wake-up of Rosetta. And I would like now to give the floor to Thomas Reiter.
So good morning, ladies and gentlemen. Welcome to the European Space Operations Center, ESOC, for another great event right at the beginning of this year. Please allow me to give a special welcome to the head of the German Aerospace Center, DLR, Professor Wörner, and the chair of our council, Jan. Welcome. Also, I would like to say welcome to the representatives from industry. Of course, representatives from media. I'm very happy that I see so many guys from all various agencies, media agencies here. For the scientific community, allow me to say welcome to Dr. Gerhard Schwem, Professor Bernd Feuerbacher, and Professor Bibring. Welcome. And also welcome to a lot of ESA colleagues here, amongst them, of course, our Director General, who is already at the main control room. We have with us Alvaro Gimenez. Alvaro, welcome, good to see you here. And of course, my predecessor here, Gale Winters. Gale, welcome here. Also, welcome to all colleagues from all other ESA centers and, of course, here from ESOC. Now, for the third time in just a few months, we would like to share with you another fantastic, outstanding ESA scientific mission. In November, we witnessed the launch of SWARM. SWARM is now in the middle of the commissioning phase. Remember, this is a constellation of 3 satellites, which are in a polar orbit. Then we had in December the launch of Gaia. Gaia has in the meantime reached its final destination, the Lagrange point L2, and is also starting with the commissioning of the scientific experiments. And all these missions are proceeding well as I speak. Now, today's event is of a different nature, and the solar system is in the focus. This time no launch, instead we follow the wake-up of the most pioneering comet-chasing mission, Rosetta. Now, why is a comet the target of an ESA mission? My colleague Alvaro Gimenez, the ESA Director for Science and Robotic Exploration, will go into more details of the scientific aspects of Rosetta. I just would like to mention here that comets are quite interesting for the scientific community because we believe that comets contain the primordial matter from the times when our solar system was formed roughly 4.6 billion years ago. After a 10 years journey through the space, Rosetta will just arrive at its ultimate destination in August this year, the comet P67 or Churyumov Gerasimenko. Rosetta was launched in March 2004 on an Ariane 5 rocket from Kourou, French Guiana. And during this long haul, Rosetta performed 4 major swing-by, or as we call it, gravity assist, 3 swing-bys of the Earth and 1 by Mars, leading to a distance of up to 800 million kilometers away from the Sun. This is even slightly outside the orbit of Jupiter around the Sun. It's an all-time record for solar-powered spacecraft. So far from the Sun, the solar arrays receive not sufficient light to produce enough electricity to keep the spacecraft fully active. And therefore, we put Rosetta in hibernation in June 2011, about 1.5 years ago. Only its computer and some heaters remained switched on to get it through the cold phase of this flight. Now today, we will hopefully, keep fingers crossed, witness that Rosetta comes out of this hibernation. And then, of course, we are looking to revive this spacecraft. In February and March, it will be fully activated. In April, we will do some payload commissioning on Rosetta. In May, another very critical operation. We need to do a large orbital maneuver, a delta V of about 800 meters per second in order to match the speed of the comet. And that will then finally match the comet orbit and the rendezvous with the nucleus. And only then we are ready for the orbit insertion maneuver, which will be completed in August, and bring Rosetta at a distance of about 100 kilometers and then slowly closing in. The relative velocity at this point will be only about 0.5 meter per second. Finally, in November, the Philae lander will be delivered to the surface of this comet. Now, approaching, orbiting, and landing on a comet require delicate maneuvers. We know very little about the comet's rotational dynamics, its actual surface properties, so we will only be able to identify a safe landing scenario when we get there. And that is, as you can imagine, a very crucial phase for the success of this part of the mission. All this makes Rosetta one of the most complex and challenging missions ever undertaken to a body in our solar system. This mission is made possible only thanks to the dedication, the passion, and extraordinary capabilities of all those who have been involved. The scientific team, the engineering teams, industry, ESA, and of course, as I said, the science community. The operation of a mission such as Rosetta is indeed a major challenge, never attempted in the history of spaceflight, and it requires a lot of experience and skills. And this experience and know-how we have acquired over the last 45 years in all types of missions in low Earth orbit here at ESOC, in geostationary orbit, missions to Lagrange points like Gaia, I mentioned before, and interplanetary missions. And this experience and know-how is unique in Europe indeed. Today, here at ESOC, we are controlling 9 missions consisting of 14 satellites, including Rosetta, and there are still 18 more missions which are currently in preparation for a launch within this decade. Now, in order to do all this work successfully, a lot of preparation is needed. My colleagues here from ESOC work together with the project teams from our partner directorates, such as Science and Robotic Exploration Directorate, and with external partners to support the preparation of the launch and subsequently the controlling of the satellites. Furthermore, you need a worldwide network of ground stations and antennas to receive the signals from the satellites, certainly from Rosetta, which is hundreds of millions of kilometers away. And a lot of software and special technology is needed in order to achieve that. Most of these ingredients cannot be bought off the shelf, but are developed here at ESOC and at other ESA centers. Now, during Rosetta's prolonged interplanetary expedition, reliable communications between the spacecraft and the Earth are essential. The ground stations of ESA's Deep Space Network, New Norcia in Australia, Cebreros in Spain, and Malague in Argentina, are used to communicate with the spacecraft and to download the telemetry data. These will be collected at the ESOC Mission Control Center here in Darmstadt, and the scientific data then will be routed to the European Space Astronomy Center, ESAC, in Madrid for initial data processing. The information will be stored there and made publicly available. For the special activities related to the landing operations, the ESOC operations team will be supported by the Lander Control Center, LCC, at DLR, the MUSC, which is in Cologne, and the Space Operations and Navigation Center at CNES in Toulouse. Thus, as usual for ESA missions, Rosetta operations will become a real united effort. Well, Rosetta mission is one of the superlatives. It's truly unique, and in William Shakespeare's word, stuff dreams are made of, only that this, hopefully, is soon no longer a dream, but reality. I'm proud to be here together with you to witness another major milestone in this unique and formidable mission, a mission very likely much bigger than we can imagine, and that may potentially revolutionize our knowledge about comets and our understanding of the origins of life. A challenge for all the partners involved and a testimony for the excellent work of our teams. I will now hand over the floor to Alvaro Gimenez to provide you with a brief overview of the mission and its scientific importance, and then followed by the experts who will take us through today's events. So thank you very much for being with us today during this important moment, and I'm sure we are all eagerly waiting for receiving the first signal of Rosetta this evening. Thank you very much. Alvaro, to you.
Thank you, Thomas, for your introduction, and good morning, ladies and gentlemen from the media, the Rosetta Project, our international partners, and those who are watching us live. Imagine you are reading something, but you cannot understand the meaning of it because you do not know the letters, the symbols, the signs that are being used. This is the situation we find ourselves when we try to tackle the big questions about our place in the universe. How did our solar system come about? How did it evolve? How did life start? We can only look to our solar system as it is today. We see that Mars is hostile to life. We see life flourishing on Earth in every corner. We observe asteroids in a belt between Mars and Jupiter, as well as the planets and the moons, but they all have changed since the last few billion years and have not allowed us to really understand the very beginning of our solar system. The signs of the past they may hold have changed too much for us to read and understand them today. Rosetta, however, will in this regard be a unique mission. Rosetta's target, comet 67P, or Churyumov Gerasimenko, comes to us, to the inner solar system, at a distance is periodically coming, but at a distance that with the spacecraft technology we can get to the comet. We can fly there. But 67P is made out of material that is linked to the infancy of our solar system. It's pristine, non-corrupted material, giving us information of the gas and dust nebula that gave birth to our entire solar system. Therefore, Rosetta can open this icy treasure trove, and it will be like opening a window in time to look back at the beginning of our solar system and at its evolution. Our Rosetta mission is therefore has the promise to become the real Rosetta Stone of planetary science, allowing us to understand the origin and the history of the solar system. Of course, the language will be different than the original Rosetta Stone, famous one. It won't be ancient Greek, which Ptolemy V spoke, nor Demotic, spoken by the Egyptian population 200 before Christ. Both used to actually decipher the third language on the stone, the Egyptian hieroglyphs, used by the priests at that time and on ancient Egyptians. It will be the powerful language of physics and chemistry that will be uncovered, and they will allow us to understand. Rosetta is absolutely unique with respect to the science result it will produce, but it's also unique with respect to operations. We are doing things nobody has done before. Rendezvous, that is fly around the comet, escort a comet on its way through the solar system when it becomes more and more active, and land on a comet. These are three firsts that so far nobody has tried, let alone achieved. Let me echo what Thomas Reiter was already saying before. What we are trying to do here is extremely difficult, extremely challenging. And I would like to take the opportunity to thank my ESA colleagues, Andrea Comazzo and Paolo Ferri and their teams, for their outstanding dedication and work done so far. Looking at the images and result of the flyby by asteroid Lutetia in July 2010, before Rosetta got in hibernation, I can only say that this was a very promising beginning for Rosetta. And this was just the beginning. As said before, Rosetta and Comet 67P might become the Rosetta Stone for planetary science. Allow me to pick up and highlight two aspects of the Rosetta science: the origin of the solar system and comets as carriers of water and life. As the origin of the solar system, knowing which elements, molecules, etc. make up 67P may reveal the composition of the pre-solar gas and dust nebula, out of which the solar system and the planets formed. The second one is that knowing the temperature and pressure regime under which 67P formed could tell us a story of the infancy of our solar system, its origin and evolution. Moreover, 67P is a Jupiter family comet originating from the Kuiper's belt with an individual and unique history. We will learn a lot about this type of comets. The grains temperature, for example, history will tell us how close they have been to the sun while traveling through the solar system. And from the isotopic ratio of the elements on the comet, we will understand in which star formation processes they have been created. Concerning carriers or bringers of water and life, we know we have a problem with understanding why we have water on Earth. I mean, according to normal theories, we should have no water on Earth, but we know we have. And the plan is, the scheme we have is that it was brought by asteroids and comets. So we are convinced that Earth experienced a lot of comet impacts in the past during the late heavy bombardment 4 billion years ago, and comets might therefore have brought water and organic molecules to Earth. We think that 10% to 40% of the water we have on Earth could have come from comets. Water, in addition, has a specific footprint with respect to the ratio of normal water to heavy water. Latest measurement of Jupiter family type comet by ESA's Herschel Space Observatory gave a ratio value which is in line with Earth water. I am very curious to see what are the measurements taken by Rosetta in this isotopic ratio and finding out if this is a source for the water we have on Earth. It is known that complex organic molecules are abundant and exist in the stellar space and in comets. But life on Earth prefers, we know, organic molecules with a certain geometrical structure, what we call left-handed structure. They are left-handed rather than right-handed for some reason. And if Rosetta finds these organic molecules there are by some chance left-handed also, we will have some indications about the connection to the beginning of life on Earth. At ESA, we have, talking more generally, a strategic approach to tackle the big scientific questions. And all our missions are linked to explore the various unknown territories of science and knowledge, trying to cooperate also with our international partners and as much as possible. In planetary science, for example, we have Mars Express since more than 10 years ago in orbit around Mars, revealing topography, mineralogy, atmosphere, detecting water, methane, so on. We have Venus Express, understanding the complex atmospheric structure of our sister planet, and coming in the near future for aerobraking to reveal lower atmosphere levels of Venus. ExoMars 2016 and 2018, together with our Russian colleagues, to make next step in Mars exploration beyond Mars Express, which is bringing the technology to land on Mars, but also allowing us to roving and especially drilling into the surface. Bepi Colombo, together with Japanese colleagues, get into the most unknown planet in the inner side of the solar system, which is Mercury, and use the Jupiter Icy Moon Explorer, which will bring us to those big satellites around Jupiter that we are sure contain big amounts of water under the surface. In addition to planetary science, we have astronomy, and you may have heard about the big and important results of Planck and Herschel, which are no longer collecting data, but a lot of information will be obtained by analyzing the obtained data in the coming years. For example, Planck will see an important release of results mid of this year. Gaia was just launched and is its operational point in space to start to produce the most precise three-dimensional map of our Milky Way. LISA Pathfinder will then prepare the technology to measure gravitational waves, and a small mission, CHEOPS, in 2017 will go ahead in the study of exoplanets around nearby stars. But a large mission, JWST, which is in cooperation with the US, will study the very distant universe. And Euclid, finally, by 2020, will get into next step after Planck, which is to probe dark matter and dark energy and try to understand what are they made of. You see, our calendar is quite full, and we work hard to make the dreams of our scientists, of our society in general, of humankind, coming true. and answering the big questions. This is only possible because we have an excellent program, an excellent industry in Europe. And coming back to Rosetta, I would like to thank Astrium as a prime of the spacecraft who built Rosetta for the work and ongoing support to the mission. I would also like to thank our member states for their continuing support to the science program, and also the various institutes in our member states who have contributed to the instruments. Although it is today just the wake up, is also the first big day for Rosetta in the many contexts, in the many aspects that we will have to look at this year. Rosetta is, because of this event, already in the mind of many people in Europe and the world, and the whole process will start today. This bodes well at this attention with the real challenges still to come when we rendezvous, scored, and eventually land on 67P. The first of all of it, Rosetta needs to wake up, and it will. Thank you.
Tu pourrais te réveiller, s'il te plaît?
En revanche, Rosetta.
Rosetta? Rosetta, réveille-toi.
Svegliati, Rosetta.
Il est l'heure.
Il faut se lever maintenant.
Allez.
Allez.
Vamos, Rosetta.
Despierta, Rosetta, que ya es hora, hombre.
Svegliati, Rosetta.
Wake up, Rosetta.
Wake up, Rosetta.
Hello everybody and welcome to the Rosetta Wake Up event. I'm Monica Jones and I'm here at ESOC in Darmstadt, Germany. By the way, right behind me in this clean room, there is the sister model of Rosetta, the comet chaser. Rosetta itself, of course, was launched into space 10 years ago, and on its long journey it passed through an asteroid belt while traveling some 900 million kilometers deep into space. Now, once Rosetta was too far away from the sun to charge its batteries, it was sent into a deep sleep. And today, 3 years after hibernation, it is time for Rosetta to wake up again and to follow the Gerasimenko Gerasimenko comet, also known as 67P. And this comet is currently on its way back towards the sun. Once Rosetta is close enough, it will send down a lander to carry out scientific analysis on the comet's surface, and that is something that's never been done before. Now, before Rosetta can continue its groundbreaking mission, it has to wake up first. And the onboard alarm clock is set to go off at 11 o'clock Central European time. That is 10 o'clock GMT. And due to the vast distance, of course, it will take some time for ESA to receive the "Hello, I am awake" signal. We expect it at some point this afternoon. So quite an exciting day ahead, and we will cover the whole event for you. Now, Rosetta is surely the boldest and most ambitious of ESA's comet missions, but let's not forget, it is not the first.
The Star of Bethlehem in Giotto's Adoration of the Magi is the first known realistic image of a comet. Painted shortly after the appearance of Halley's comet in 1301, the European Space Agency paid tribute to the Italian artist's work centuries later by naming its first comet-chasing spacecraft Giotto. Launched in 1985 on an Ariane 1, Giotto was ESA's first deep space mission. A year later, Giotto made history when, as part of an international fleet of 5 spacecraft, it approached Halley, which was once again returning to our skies. Giotto got within 600 kilometres of the comet, producing a number of spectacular images, including close-ups of the comet's nucleus. Halley, like Comet 67P Churyumov Gerasimenko, originated from the icy Kuiper belt beyond Neptune. These dusty cosmic snowballs orbit the Sun and may have brought water and organic compounds to Earth. We know from space missions that each comet has a frozen nucleus, often only a few kilometres across, and that when the comet's orbit approaches the Sun, it develops an atmosphere or coma. The solar wind pushes this atmosphere into a trailing tail, actually two tails of dust and gas that can stretch for thousands of kilometres. Throughout history, comets have been seen as omens of doom or success. But when it comes to learning more about comets, the legacy of Giotto is definitely a successful one.
And I'm just outside the main control room now. The main control room you can see through this glass window behind me. Before I go inside, I would like to talk to the gentleman standing right next to me, the Director General of the European Space Agency, Jean-Jacques Dordain. Now, in this film before, we just seen that obviously ESA's done quite complex missions before. Are you still excited?
Yes, oh yes. Nervous, excited, yes, and confident. But it's true that Rosetta makes a new step because with Giotto we went to a comet, but we were there just for a couple of hours. Now we are going to be with the comet and on the comet during almost 1 year. So we shall certainly learn much more than with Giotto.
Now, what exactly is Rosetta all about? Because you mentioned Giotto already. There was already a comet chaser, but Rosetta is a step further, right?
Oh, much further, because this time we are going to the comet, and it's still a long way. But we shall be around the comet this summer, and we shall land on the comet in November, and after that, until at least mid-2015, we shall be on the comet and around the comet to see how the comet is living for more than 1 year. So that is certainly a big difference. It's a much bigger mission than Giotto. Risky, because nobody has done that before. And but this is the price to pay to learn a lot about the origin of the solar system and maybe also the origin of life. So I think that this is certainly an important question.
So there's a lot of science going on as well, because a mission like that is very costly, very complex. It's a European mission, and they don't just happen by chance. They need to have some real serious scientific purpose, right?
Absolutely. And there is 21 instruments on scientific instruments on board Rosetta. Just to say that the science program of ESA is the only program where all member states have to contribute. So this is a collective endeavor. And it's more than that, because the ESA is also cooperating with national agencies and scientists. And with 21 instruments, we have almost all member states on board as scientists. And we have also scientists from the United States. And the lander also has been developed under DLR with a strong participation of CNES and ASI, so national agencies. So we are all together on board Rosetta.
Now, when we look at daily politics, we know that many players in Europe as well as across the Atlantic, that doesn't always make things easier. How do you keep everyone on the same page?
I think that the best is to have a challenging objective, a common and challenging objective. And I can tell you that when we have a common and challenging objective, much easier to make all these actors working together. And this is what we are doing at ESA.
Now, let's get back to Rosetta again as well, and its role for the European Space Agency. We said earlier, obviously, we established that you've conducted many big, very important and complex missions. But where does Rosetta fit in that context?
Well, I think that, yes, you are right. I think that all our missions are fantastic. So, but Rosetta is special in the sense that we are very far away from planet Earth, and so far away that we were at a place where the sun was very dim, and it was not possible to keep Rosetta alive during that period. And this is the reason why we have hibernated Rosetta, just because it was too far away from the sun.
And today is the big day where we have to wake up Rosetta, which will happen when I look at the clock in about 8 minutes. So Jean-Jacques Dordain, thank you very much for the moment. And in 8 minutes, we wait for Rosetta to wake up. In a moment, I will go into the main control room, which is at the heart of ESOC. And ESOC, of course, is the place where pretty much all of ESA's missions are being controlled from currently more than a dozen.
The European Space Operations Centre, ESOC, at Darmstadt in Germany is where ESA operates most of its satellites, be it in low Earth orbits for the swarm satellites, medium Earth orbit for Galileo, deep space planetary orbits for Mars Express and Venus Express, or even further out in deep space as for the comet-chasing mission Rosetta. Since its creation in 1967, ESA's Flight Operations Control Centre has been handling spacecraft through all the complex mission phases. This includes mission analysis, flight dynamics, simulations, monitoring performance, telemetry and communications, and maintaining all onboard software. ESOC also stores some of the spacecraft's scientific data on servers before transferring them to the Science Operations Centres in Madrid. ESOC controls ESA's tracking station network ESTRAC, which allows the agency to communicate with its satellites. This worldwide network consists of 10 ground stations in 7 countries, from South America to above the Arctic Circle. ESA's most powerful deep space ground stations are the 3 35-metre antennae in Australia, Spain and Argentina. These will help track Rosetta in deep space 800 million kilometres away. In May, ESOC will control Rosetta's rendezvous manoeuvres so that the spacecraft reaches the comet in August. Then, after ensuring Rosetta begins orbiting and mapping its composition, ESOC will enable the Philae lander in November to become the first ever probe to land on a comet.
And I'm now inside the main control room, which is quite exciting. We also get a good view of the countdown clock here. It's less than 6 minutes to go before Rosetta will wake up. Here with me now is ESA's Operations Department Head Paolo Ferri, and you've been with the Rosetta spacecraft operations team from the very beginning, so you can tell us perhaps a few of the main highlights of this mission.
Well, apart from the many years of preparation, which were tough enough, the launch of 2004 was the first highlight. And then we thought we would have a very quiet cruise. This, of course, didn't happen. And we have many already planned events, 3 flybys, where you work for many months, and then for a few hours the work then is finished, and that's what you've been preparing for. We had 2 fantastic flybys. Well, we have 1 flyby of Mars, which was extremely critical. In 2007 we came to 250 kilometers of the surface of Mars. This was really fantastic. And of course the 2 scientific highlights, which were the flybys of 2 asteroids, first Steins and then Lutetia in 2010. And Steins was also very exciting. For the first time we used the navigation camera for steering the attitude of the spacecraft, and we found out that we had a lot to learn. So the operation worked, but thanks to that we had a fantastic flyby of Lutetia, which went even better.
Okay, and another highlight today, of course, with the wake-up event of Rosetta. Now, it doesn't happen that often that we are allowed inside the main control room, so perhaps we can make use of this opportunity. And could you take us through some of the key positions here?
Yes. First of all, it's a very special setup. It's not the same that you see when we have a active operation at launch. Here, the majority of the work for the wake-up was done 2.5 years ago. So there's very little to do today up to the moment where we get the signal. The team is also smaller. So we have a setup where we will have the flight control team in this area here, and the spacecraft operations manager and part of the team who are actually already sitting there in that part where normally the flight director and the project representative representative are sitting. And on your back, there's the other area that deals with the ground segment, ground stations, communications, computers. The ground operations manager, the software coordinator, they will be sitting here. It's not many people. As I said, this room is big enough for big launch events. This is scaled down to the lower level of activities of today.
And yet you handle objects that are some 900 million kilometers in deep space far away. Well, thank you very much, Paolo Ferri, for explaining it all to us. Rosetta is due to wake up at in 3 minutes' time. Let's make the most of that time now to look at what's been happening on Rosetta's journey so far.
10 years ago at Kourou in French Guiana, the Rosetta spacecraft set off on a breathtaking mission into deep space for a rendezvous with a comet. Comet 67P Churyumov Gerasimenko is around 3 by 5 kilometers in size and is known as a Jupiter family comet because its orbit around the Sun is controlled by Jupiter's gravity. Some of these icy space rocks are ejected by collisions or gravitational changes and become comets. Comets help scientists understand the origin and evolution of the solar system, as well as the role comets may have played in seeding the Earth with water and the complex molecules that formed life. In order to reach its target, Rosetta played a game of cosmic billiards with 2 of the planets in our solar system. It swung by the Earth 3 times and once around Mars for a gravitational push onto its long journey. During the trip, the spacecraft then made flybys of 2 asteroids. In 2008, Rosetta imaged asteroid Steins, one of the millions of asteroids orbiting the Sun between Mars and Jupiter. Steins revealed itself to be a diamond-shaped rock covered in impact craters. In 2010, Rosetta met up with a different asteroid. Letitia is believed to be around 4.5 billion years old, a remnant from when the solar system was formed. Covered in grooves, fractures and fault lines, one of its 350 craters stretches for 57 kilometers. The remains of a dramatic collision. Its composition also hints at a metallic core. But the main prize has always been a comet. And after Rosetta entered deep space, continuing its long comet-chasing journey, it put all but essential operations into temporary hibernation in June 2011. Now, 800 million kilometers away from Earth, Rosetta is preparing to wake up.
Okay, and with less than 45 seconds to go, I'm joined here by Andrea Akumatsu, Rosetta Spacecraft Operation Managers, and he got a model of Rosetta right behind him.
That's right. This model was made by my father in '99, and it helped me to visualize the spacecraft when I was familiarizing with it.
Okay. Now, Andrea, before we talk further about what's happening on Rosetta, I think because it's only 14 seconds until Rosetta will wake up, which is of course something that happens some 900 million kilometers far away, deep in the dark space. So we can't see it, but we prepared a little video in order to show you what's happening right now. Let's take a look.
Once the spacecraft receives its internal alarm call, Rosetta will begin to wake up in distant deep space after sleeping for 31 months. First of all, the star trackers will begin warming up. Its thrusters will fire and the spacecraft's rotation will begin to slow. The solar arrays will turn to face the Sun so that it can power up all the 21 instruments on board. The slower rotation will begin. And once the star trackers determine the spacecraft's attitude, Rosetta will rotate towards the Earth, as will its antenna. After several hours warming up, Rosetta will be able to send a signal to the European Space Operations Centre. This tiny signal will take 45 minutes to travel 800 million kilometres.
A bit about it and then I'll ask you a question. All right, then. We're back here now. So now you have an idea what's been happening some 900 million kilometers in space. And we're back with Andrea Accomazzo and his model, which fell a bit short. I think you were just about to explain to us what we can see here.
Yeah, this is a model that I asked my father to make it in 1999. When I had to familiarize with the spacecraft, we were working on the backup modes of the spacecraft, and this helped me a lot in visualizing it, what could happen with the spacecraft.
Is that the reason why you told me earlier that you were a bit reluctant about actually putting Rosetta to sleep in the first place?
Well, this hibernation was never attempted before, but before a nominal mission. It's the first mission that does anything like this. It's not something we feel comfortable with, but we had no other choice. We had to do it. There was no other way to fly to this comet and actually reach it.
Now, when the alarm clock rings for me, I'm usually not that eager to get up immediately. So how long will it take for Rosetta to stretch and actually get down to work?
Well, Rosetta is a bit similar as well. It cannot do immediately the toughest operation of the hibernation exit, so it has to warm up a bit. This will spend a couple of hours, actually 6 hours, to warm up some electronic units we need later on. And only at the end of this warm-up phase will actually do the wake-up itself, spinning down the spacecraft.
Are there any particular challenges to watch out for in that phase?
Well, the spacecraft has many challenges. Today is a big operational day, but the biggest challenge is on the spacecraft itself, has to stop the rotation, to stop the hibernation, to regain knowledge of where it is, where it's pointing, and actually drive itself and the IGN antenna to point to the Earth. And then only then we can get the signal and see that it's back.
Okay, so definitely exciting. And I think, Andrea, quite a lot of what you just explained, what's happening right now out there, is something that we will try to visualize now.
When ESOC receives Rosetta's signal from deep space, it'll upload commands to ensure that the spacecraft begins a series of comet rendezvous maneuvers in May. After arriving at the comet in August and braking to match its speed, Rosetta will become the first spacecraft to fly alongside and escort a comet as it approaches the Sun. The spacecraft can then observe any changes in the comet from an unparalleled viewpoint. Its orbit has been specially planned, flying around 3 corners in a series of highly demanding operations. These allow Rosetta to examine the comet from all angles and in increasing detail. They also allow the spacecraft to remain a mere 30 kilometers from the comet when Rosetta later enters a closer circular orbit. Rosetta will begin mapping the comet in August. Scientists will also study images from Rosetta's onboard camera so that in October they can decide on the best landing site. The next stage will be another first when the Philae lander separates from the orbiting spacecraft and performs a controlled descent to become the first ever probe to land on a comet. Philae is a portable laboratory carrying 10 different scientific instruments. All of these instruments will start work immediately after touchdown for 5 intense days of measurements. This will include imaging the local landscape and drilling beneath the surface of a comet for the first time. Samples will be analysed and the results will be relayed back to Earth via Rosetta. The spacecraft will then continue monitoring the comet long after the lander has completed its task to provide 18 months of invaluable information about this primitive remnant of our solar system.
And as ESA's Director General Jean-Jacques Dordain said earlier, missions like these don't just exist for their own sake. They happen for a vital scientific purpose. In Rosetta's case, it is to look at the makeup of a comet. But once you've seen our next video, you might wonder why it is necessary to go all that way when at the University of Bern in Switzerland, they actually made their own comet.
So now we're going to go down into the labs downstairs. We're going to make ourselves a comet.
There are millions of comets beyond Pluto, and though not all the same, they share similar ingredients: water ice, frozen gases and dust. So to cook a comet, it's a simple recipe.
First of all, we need to create a sort of a liquid, and so we're mixing our 50% of our comet, that is this water ice, we're mixing it now with a little bit of liquid nitrogen, and we're using here carbon black. It's finely divided carbon particles. And now we do some comet cooking. Well, the liquid nitrogen is currently sitting at around minus 200 degrees centigrade, and that's keeping the water ice from evaporating and keeping it from sticking together. What we now do is that we tip the mixture into a sort of a mold, and that is a fake comet, ready for experimental studies.
At the University of Bern, the fake comet is about to go under scrutiny.
So we're taking this particular sample and we're going to test it, put it and simulate as if it were in space.
Scientists can use their readings to help interpret data from ESA's latest comet chaser, the Rosetta mission.
That looks a bit brittle to me, that fake comet. But here I am with two gentlemen now who can probably explain to us why cooking a comet just won't do. Matt Taylor, he's Rosetta's project scientist at ESA, and Mark McCoffran, he's senior scientific advisor at ESA's Science Directorate. I would like to start with you, Matt, and obviously the first question is why travel all that way when you can just cook a comet?
Well, we're going to go somewhere where it's real. We're going to sample a comet for real. And Rosetta is going to do that for us. It's going to provide us with an unprecedented characterization of a comet. This is groundbreaking science we're going to do. And that will lead us to a journey back in time to the origins of our solar system. And from that will provide us with a better understanding of how the solar system was formed and its subsequent evolution to how we know it today.
But we already have something that's called the Big Bang Theory. Will Rosetta add anything to that or change it perhaps?
Well, it's more, we're looking at, on the smaller scale, on how, where we came from, the evolution of our own solar system. And comets are looked upon as a kind of time capsule back to the beginning of the solar system. So we look at those as mapping back to how we began and where we came from. So if we look at, well, let's start with the evolution of the solar system. About 4.5 or over 4.5 thousand million years ago, the proto-sun was formed out of a collapsing cloud of dust and gas. From the subsequent accretion and collisions of the material around that young sun, the planets were formed. The asteroids and comets we know today are kind of the cosmic leftovers, the debris that was left over from that formation process. And of those, comets are particularly fascinating because they were thrown out into the outskirts of the solar system, into deep freeze, the Kuiper belt and the Oort cloud. Every so often, under gravitational perturbations, the comet is brought into the inner solar system within our reach. Now, for Rosetta, the target comet, 67P, Churyumov Gerasimenko, that's one of these comets. It's in the inner solar system. We chose that one specifically because of its orbit around the sun, brought us the capability of going to rendezvous with it, so therefore we can go and open one of these cosmic time capsules.
So these comets, 67P included, basically carries the DNA of the birth of the universe within it. But what do we do with the data once we've cracked that DNA?
Well, first of all, we have to go and sample the comet, and this is what Rosetta's designed for. It's specifically looking at the physical and chemical constituents of the comet. That will give us knowledge on how the comet was formed, where it was formed in that early solar system, and also its subsequent journey within the evolution of the solar system in general. We'll also be able to connect it to the planetary formation and how things went on with the planets themselves. In addition, the elemental makeup of the comet can be considered star stuff. It really will provide us knowledge of the formation processes within the sun itself.
Okay. Will it also tell us something about the evolution or the start, the beginning of life on Earth?
Well, I think there's two things that we're going to be looking at. There's water and also the building blocks of life that you were talking of. In particular, if you're looking at we consider the big bombardment, the heavy bombardment that went on in this infancy of the solar system, where cometary impacts of the Earth were much more frequent than they are today. So if we take water has a particular characteristic isotopic footprint, and comets are laden with water ice. ESA's Herschel mission recently showed that for particular classes of comets, this isotopic footprint was very similar to what we find on Earth. So we're looking forward to seeing what Rosetta will do in that area. Now, for the building blocks of life, we look at complex organic molecules, and comets are laden with these. On Earth, complex organic molecules are the building blocks for life, amino acids. We have instruments that will specifically look at this on the comet. One of the characteristics we look at with the instrumentation is the handedness or chirality of these molecules. On Earth, there's a preponderance, a preference for left-handedness. So by connecting this heavy bombardment in the early solar system, the handedness of these molecules will be looking at making that connection with the formation or delivery of life on Earth, which is nice.
Well, it's certainly a lot to look forward to once you've got all the data and draw all the conclusions. Matt, thank you for now. If you would be so kind, because I'd like to ask a few questions to Mark, if you just swap positions, because my arm, I'm afraid, isn't long enough to reach you, Mark. And from what I heard, you are, like everyone here at ESA, but you in particular, you really like to ask the big questions, don't you?
The space science program here at the European Space Agency is addressing exactly that, very big questions. The origin of the universe, how did it all begin, how's it evolved, the birth of galaxies and the stars within those galaxies and the planets which go around those stars. We now know, for example, there are thousands of planets going around other stars in our Milky Way. But of course we also want to study our own origin. How did the solar system we live in today and its 8 planets and all of the other constituents, how did they come about? How did they arise? So we have missions which are studying many of the planets. We have a mission at Mars, Mars Express, Venus. We have a mission shared with NASA which is at Saturn and looking at Saturn and its moons. We're also studying the Sun in great detail. We're building new missions. We're going to be going to Mercury. We're going to be looking at the Sun from very close up. And we're going back to Mars as well. So Rosetta plays a part in that whole picture, but it plays a really important part because many of those studies we have in the solar system are looking at it as it is today. Rosetta gives us clues by unlocking this time capsule how it was then, right back at the birth 4.6 billion years ago. So piecing this whole picture together will allow us to find our place, not only in the solar system, but in the universe.
And these are questions, of course, that's been bothering mankind for ages and ages. So can we look forward to some really, tough answers, world-changing answers? What do you think? What do you expect?
Well, I think so. But of course, when we go to the comet, we're not going to open a literal treasure chest that's going to have a box of a book in it that says this is how it all began. So there's a lot of science to be done to look through the clues and sift things out and compare and contrast with other things that we see in our own solar system, other moons, other planets, but also with extrasolar planets in systems outside of our solar system. So there's going to be a lot of work to try and piece it all together. But of course, at the same time, it's a great adventure. Just the idea of going to a comet, catching up with it, grabbing a hold of it and riding the bucking bronco as it goes into the inner solar system. I think people understand that as well.
Mentioning of grabbing something, you've got a jug, which right now we can't see. If you could just pick it up for us, because I'm very curious to find out what this is and why did you bring it today?
Well, this is something traditional here for the Frankfurt, the Darmstadt area, and this is what's called a bembel. And a bembel is full of Apfelwein. So this is cider. And the connection for me, I'm from the southwest of England, from Devon, and some of my friends who live down there reminded me a couple of days ago, they went out and did a thing called wassailing. And wassailing is a time in the winter where you go and you wake up the apple trees, you wake up the cider trees to get them out of their slumber so that in the autumn they come with a good harvest, a good product at the end of the year. And that's Rosetta. So we're here this morning to wassail Rosetta, to wake it up, to drink to its health, and hopefully have a productive autumn when we actually get to the comet and then in November land on it.
I say cheers to that. Cheers to Rosetta. Thank you very much, Mark. Thank you very much, Matt. That is all from us for now. We're scheduled to receive Rosetta's wake-up signal at 6:45 CET or 5:45 GMT. We'll be back about 15 minutes earlier to that to bring you up to date. Of course, you're invited to follow our afternoon program via web stream. Either way, we'll see you soon.
Wake up, Rosetta!
But I'm even more nervous than before, because now we are waiting, right? And it's not just probably stage fright that I have. It's exciting, definitely the mission. Our next speaker is Johann-Dietrich Wörner, the chair of DLR and also the chair of our council. The floor is yours.
Yeah, thank you very much, and good morning, everybody. So my task is to talk a little bit about the German contribution to Rosetta. But before doing so, I would like also to come back to the question why. Why are we doing this Rosetta mission? This is a question you can hear from everywhere and from everybody. And of course, fundamental research sometimes has this question at a focal point. Just to remember and to remind, was it important to understand that the Earth is not flat? It was fundamental research finding out that. Or wasn't it interesting to understand that not the Sun is moving around the Earth, but that the Earth is orbiting the Sun? Looking to Einstein, Einstein found the relativity theory. Is it worse for our daily life? Yes, it is, because without that relativity theory, without the understanding that time is depending on gravity and speed, our navigation systems would be wrong, would have an error of about 500 meters within 1 hour. Or look to Faraday. Faraday, who invented how to produce electricity, he got a visit of the British finance minister, of course asking, "Good man, what is it good for, what you are doing here?" And Faraday said, "I don't know, but I'm sure you will tax it." A third example, we are discussing about global change, about climatic changes of the Earth. It was not found by some laboratory experiments on Earth. It was found by looking to Venus, because the greenhouse effect of Venus is even stronger than that one which we have on Earth. So the discovery of the unknown sometimes, and in very many cases, leads really to results which we can use, which we have to use on Earth. So our global challenges like climatic change, mobility, communication, energy, shortage of resources, demographic development, conflicts and catastrophes, and health, all of these challenges need research. And some of the research has to be done in the very unknown areas. So not only looking how to develop the next mobile phone, which has some new ideas what can be done. And there are very many questions in our universe. Dark matter, dark energy. What about the origin of our universe? What about some peculiarities in our solar system? All of this can be put together in the short motto, knowledge for tomorrow. And of course, I'm an engineer, and of course, I'm totally stimulated by these projects, but we should also look to other people. For instance, a philosopher who said, "We will not cease from exploration until we come back to where we came from and see the place for the first time." So T.S. Eliot said that sentence, and it fits perfectly to what Rosetta is doing. Another sentence which is very famous and very well known is space, the final frontier. These are the voyages of the starship Rosetta. Not its 5-year, but its 10-year mission, and not to explore strange new worlds, but to explain strange old worlds, because Rosetta is looking to a very old world, and Churyumov Gerasimenko is an interesting place. So, as you heard today about all these ways what to do, and about the Rosetta orbiter as well as the Rosetta lander, both of them having important names. You heard about Rosetta linked to the Rosetta Stone, which gave us the possibility to understand the old letters, the hieroglyphs. And at the same time, the lander is called Philae, because Philae is an island of the river Nile. It's the island of the time, and there is an obelisk on this island which gave also some hints in understanding the old letters. So therefore Rosetta and Philae are really coming together. The German contribution to this mission is, and of course always money is the question which is asked at the beginning, is about close to 300 million euro. So this 168 million comes from the German ESA budget, so Germany is paying to ESA a contribution, and 168 million out of this was used for the Rosetta mission, and another 127 million euros comes from the national German contribution, so we have different budgets in Germany. In addition, of course, all these research entities, be it Max Planck, be it DLR, contributed with their stuff to the mission. From the German side, we have on the orbiter some hardware which came from the German side, for instance, for the visible and infrared thermal imaging spectrometer. We have some involvement in OSIRIS, which is the optical spectroscopic and infrared remote imaging system. We are involved also in the Rosetta Plasma Consortium and the Rosetta Orbiter Spectrometer for ion and neutron analysis. I cannot give you all the details because I don't know them, but I know what I have written here. So, in addition, we have, of course, the lander. The lander is within this consortium of Rosetta overall. It's a German lander. We have the system lead on the German side. The lander control center is German. The lander structure, the thermal system, the active descent system, you saw it in the video. Also the assembly, integration and validation was done by Germany. The landing gear and the anchoring harpoon. I don't know whether you saw it on the video. Because of the small gravity, the low gravity of Churyumov Gerasimenko, the small lander has to immediately anchor itself. And there are small harpoons inside, and hopefully these harpoons will put the lander in a stable position. Then we have multi-purpose sensors for surface and subsurface science, and of course special landing imaging systems, as well as electric sounding and acoustic monitoring experiments. All of this is future. It's flying since 10 years without any maintenance. You cannot put it to your workshop within this 10 years in a harsh environment, and hopefully it will reach the Churyumov Gerasimenko as in an orbiting phase as well as landing on the comet. But we can also, and we are very lucky about that, and happy also, we can also give you already results on Earth from Rosetta flying to Churyumov Gerasimenko, because there is a sensor on board which is there in order to investigate the tail of the comet, and the tail is gray. So therefore special sensors were developed, and these sensors were brought back to the Earth, no, not physically, but the idea, and are now used for forest fire detection. So these sensors can exactly differentiate between different types of gray. So there are in Brandenburg, close to Berlin, already more than 160 installations which are looking above the forest to see if there is any smoke, and then to decide whether this smoke comes from a fire or whatever it is. So there is this, as I call it, Teflon pan effect already. Teflon pan does not come from space, but the effect is there. But I would do all these experiments, this exploration, even without this effect, because curiosity should be within our heart to discover what is so far unknown. And by the way, Rosetta, and this is far beyond the German contribution, is also an example of how space is done today. If you look back to the 50s of the last century, we had a confrontation, and space was steered and controlled by national vanities and Cold War, Kennedy and Khrushchev. Today, we have a global cooperation, and Rosetta is a global cooperation far beyond just France and Germany. It's either the European Space Agency, but also the Americans. The NASA is taking part into the Rosetta mission, and therefore I see the future. Competition is still a driver. It makes things better, it makes things faster, but cooperation is an enabler. Thank you very much for your attention.
Thank you very much, Professor Wörner. And now we come to the interactive part of the program. I told you before, you will have ample time to engage with the experts. And that's now, so to say, the start of the question and answer session. And there are colleagues here in the room who will hand you a microphone, if you are so kind to state your name, your affiliation. But of course, you don't ask me the question, so therefore I have to kindly invite the speakers of today, that is Mr. Dodin, Mr. Gimenez, Professor Wörner, Professor Reiter, to the stage, because you're the ones who have to answer the questions. Can you please come? And then please lift your hand. Who has the first question? Oh, that bears for an interesting question and answer session. I know probably you're all waiting for individual interview opportunities afterwards, but here you will not get this gentleman so often on stage for your questions. So, photos. No questions? Oh, come on. Hello. Wake up. I mean, Rosetta does its job. Yes, but there was one. Oh, no, there is a question over there.
Hi, my name's Rampal Gill, and I work at in Madrid for ESOC. And my question is, why is Rosetta being woken up today? Why not yesterday? Why not tomorrow? And why at 11?
I think this is a question for Alvaro.
Well, it was planned a long time ago. That was the day that it was programmed to have it, and is linked to how close we get and having the time now to do the preparation and the commissioning again of the instrument, checking everything is working, and then prepare for the rendezvous of the comet 67P.
Thank you.
Any other questions?
Maybe we ask some questions.
Here in front. First row.
Very much. Morning, Robert Vogel from the Perry Roden magazine. Can you please tell me something about the energy supply of the probe? We already know that Rosetta is too far away to get enough power by solar arrays. So how does it work? How does it function? And do you get enough supply now at the comet with Rosetta approaches the inner solar system?
Yes, we get to the comet so far. We wanted to go there, and that's why the hibernation and everything you heard about. But we go so far because we want to get to the comet when it's less possibly active, so that there is no activity of the comet, of course, hinder landing. And that's why we want to avoid that as much as possible. And we will, of course, map the nucleus of the comet before trying to land, or dock, as you may prefer to call it. And that needs we get there so far. And then we escort the comet. We will be flying around the comet, and we escort it until we get to perihelion, so that we will see how the activity develops and evolves in getting close to the sun. And that is unique composition, because we have never done that near to a comet. So that will be the other aspect that we need. For the landing, the docking, we will get as close as we can without, again, hindering the healthy and safe of the orbiter. And then we just deploy the lander in a process that will take 4 hours, around a little bit more than 4 hours, to get to the comet, get the harpoons to grab the comet, and then to start the science there. Then how long we will be doing science on the comet together with the orbiter. The orbiter will be escorting the comet until perihelion and beyond, so before, until the end of 2015 essentially. But how long will the science in the comet be done depends on many aspects, and many of the aspects has how activity will develop and how the comet will be able to get or not energy from the sun, or just use the batteries that will be charged before sending it to the comet. All this will be just known at that time. It will be a difficult time, and then for how long we will be doing science in situ in the comet depends on that, on what happened then.
Maybe if I if you allow me to say also a few words on energy supply. I think the development of the solar panels, specifically for Rosetta, being working on such a remote distance from Earth, required, of course, the development of very efficient solar panels which work at extreme low temperature. Well, in general, solar cells work better if they are at low temperature, even if they are closer to our sun, further away. But this is one of the, I think, the big achievements. You see that compared to other satellites, let's say Earth-orbiting satellites, you see that the solar panels really stretch out very widely in order to compensate for that. I think at that distance, if I remember correctly, the intensity of the sun is about only 4% compared as to here. So you need, of course, these very high efficient solar panels. And as we know, and I think Alvaro and Mr. Wörner, Professor Wörner also mentioned that it's an example of technology that is developed for a scientific mission, but which is of course of high importance here on Earth. We all are looking for alternative energy supply, and solar panels, of course, with highly efficient arrays are part of it. Another aspect is, of course, that this technology might be used in this Jupiter mission of Jupiter icy moons that Alvaro mentioned. Nevertheless, I believe we need certain technology which is not yet available in Europe. That is the availability of radioisotope thermal generators for remote areas, not only far away, very far away from the sun, but just imagine if you go to places, either Mars, Moon, or wherever, where you are in the shade, you need to have other energy sources, and this is something which actually Alvaro is facing in one of his programs, looking to development of this RTG technology.
Thank you. Any other questions? Oh, yes.
Norbert Peiler, Airbus Defense and Space. My question is, do you have plans for cometary mission beyond Rosetta?
Well, the scientists have. Now, now that we can do that mission in the near future is not clear. But of course, like any time you explore a place, an unknown place like comets, and measure that, I'm sure we will find things we don't expect. And that we would dream to go back again with reinforced techniques and better experiments and so on, and that will be a matter of the future. But let's first do it and then find out what kind of mission we will need in the future so that we can dream something beyond Rosetta.
Okay, let's consider this to be the last question. Thank you, gentlemen, for joining us.
I would like to put one thing. I would like to say one additional word which was not covered so far. The launching was mentioned. It was an Ariane 5. And this is for us, for the German side at least, we're always saying if we are talking about autonomy in transportation, then it's very nice if Europe can also transport spacecrafts like this in the space. This is therefore we are really convinced that Ariane 5 and also further development of Ariane 5 is important for the future. It was not covered, it was mentioned, but I just would like to say that we should not forget that launching is always the base of all these space activities.
Thank you very much. And the program foresees now a break, and I think that's also a good one. Probably we need all the sugar in our blood, so there is something to eat outside, and you can go down to the canteen. And we resume our program at 2 o'clock with the scientific presentations. But as far as I think you want to talk on an individual basis to all those experts here, you need not to grab them directly. We have colleagues here. There's, for example, Nicola you can talk to. There is Paul. Somewhere here there is Bernhard and Andreas. So if they could shortly wave their hand, then please talk to my colleagues and they will arrange for the interviews. We need to coordinate this properly in order to get the most out of you and also for the experts. For the time being, thank you very much and see you again at 2. Thank you.